Welcome to Training Module 7 in Statistical Analyses, Topic 7.6, Hypothesis Testing, Comparing Groups. The objectives of this session are for you to be able to decide when and how to perform a t-test, a z-test, a two-sample t-test, both paired and independent samples, and an ANOVA, and to know what basic assumptions are embedded in each test. You'll be able to perform each of these tests in Stata as well. There is Stata syntax or a do file available for this section. Suppose that we are looking at the 10% random sample of mixed data containing 1,181 children, and we want to know if the true average age of children in the sample is different than 3 years of age or 36 months. To do this, our null hypothesis would be that the sample mean is the same as 36 months, and our alternative hypothesis is that the mean of our sample is different than 36 months. In science, we are constantly testing the validity of our guesses or hypotheses about a population parameter of interest. It is much more difficult to show that a claim we make about such parameters is true, but far easier for us to provide evidence against these claims. Therefore, our goal in hypothesis testing is not to show the correctness of claims or to prove that the null hypothesis is true, but rather to show evidence against a claim or to show that the null hypothesis is not true. In this example, we want to see if there is enough evidence to reject the null hypothesis that the mean age of our random mix sample is the same as the average age of 36 months from some larger population. In this example, let us imagine that we know the mean age of children in the total population from which the mixed sample is drawn is 36 months. We then take the random 10% sample of the mixed data, calculate the average age in months, and see if the sample mean is close to or far away from the population mean age. The central limit theorem tells us that if the null hypothesis is true, the distribution of the sample mean is normal with mean mu naught and standard error. We need to set a threshold to determine which values are close and which are far away or extreme. And if you recall from Module 6, an observed sample mean is extreme if the probability of observing this value or a more extreme value is small. The threshold values depend on the spread or variance of the data. For example, when the variance of data is relatively small, as shown on the top graph, the probability of observing a sample mean of x bar 2, or the area under the curve to the right of x bar 2, is much smaller than the probability of observing the same sample mean of x bar 2 in the bottom graph, which is a random variable with larger spread or variance. As review from Module 6 again, we set a reasonable threshold where the probability of observing a sample mean that is as extreme or more extreme than the population mean is 5% or 1%. We call this threshold the critical value of the test. The probability of getting a value more extreme than the threshold or critical value is a significance level of our test, which we call alpha. Sample means that are beyond this threshold and what we call the region of rejection are considered statistically significantly different than the population mean and lead us to reject the null hypothesis. Because the probability of observing an extreme mean depends on the spread of the data, we must first standardize the data, assuming the null hypothesis is correct, and then calculate the probability of observing the extreme values. We then calculate our test statistic, here a z-score, and use a standardized table to find the probability of obtaining our value. This z-score calculation requires the sample mean and population mean, as well as the population variance and the sample size. You may use other tests to compare means and proportions. To specify the test statistic, we need to know about our sample and sampling distribution. We'll use an example of a z-test first, in which we compare one group, in our case, the children in the 10% random mix sample, to a norm, which is our population mean age of 36 months, assuming the sample has a normal distribution. In the next slide, you'll see that we know the population variance. If we did not know the population variance, we would use a t-test. You may also use t-tests for single means or for tests of independence, or chi-square goodness of fit test or test of independence, as well as others. It depends on your hypothesis, but each should have an underlying distribution of which you can compare means or proportions. Returning to our example, we set mu to the average age in months of children in the mixed population. Our null hypothesis is that mu is 36 months, and our alternative hypothesis is that mu is less than 36 months. We'll assume that the standard deviation for age in the population of children is 17. Therefore, sigma or variance is 17. We have 1,168 kids in the sample with data for age in months, and our observed sample mean age, or X bar, that we've calculated is 30.17 months. First, we compute the test statistic. Because we assume a known population variance, we can use the central limit theorem and assume normality. Our test is then a z-test, where X bar is our observed mean age in months of 30.17, and we subtract mu naught, which is the population mean of 36 months, for our numerator. In our denominator, we take the variance of 17 and divide it by the square root of our sample size, n. If we complete the equation, our test statistic is negative 11.70. We then find the probability of extremeness for our test statistic, and we call that the p-value. We calculate the test statistic by hand. When we calculate the test statistic by hand, we have to use a z-score table, which I've not included here, but we did go over in Module 6.6. Consulting a z-score table, we find that the p-value for negative 11.70 is less than 0.00001, which is certainly smaller than the significance level of our test of 0.05. So we conclude that there is enough evidence to reject the null hypothesis. To summarize, if the p-value is less than the significance level, or alpha, that you set before testing, and the test statistic is more extreme than the critical value, there is enough evidence to reject the null hypothesis. If the p-value is greater than the value of alpha, or the test statistic is not more extreme than the critical value, you fail to reject the null hypothesis. Now that you've reviewed the steps in hypothesis testing of a sample mean, you can do it in Stata. Returning to our example, the variable CAGE, C-A-G-E in all capital letters, is the child's age in months. The z-test command will test the null hypothesis that we enter, in this case, that the mean of the CAGE variable is equal to 36 months. So if we enter the command z-test in the command line, we then type the variable CAGE, for which we want Stata to calculate the mean, and then type the equal sign twice to indicate is equal to, and then type 36. We also type the comma and set the standard deviation, or SD, to 17 months, which was our known variance. If you do not know the variance, it will set the standard deviation to 1. We run the command and we'll get the output you see here. We can check and see that it ran the z-test on 1,168 observations, and our observed mean age is 30.17, or 30.18 if we had rounded, and the standard deviation is set to 17. Our 95% confidence interval for this mean is 29.204 to 31.17. 15387. We can see that our z-score is outputted below the table and is negative 11.7024. At the bottom, you can see that the p-value for the alternative hypothesis that the mean is less than 36 months is less than 0.00001, so we can reject the null hypothesis that the mean age is equal to 36 months. In the middle, we can find a p-value for the alternative hypothesis that the mean does not equal 36 months, and on the right, we see that there is not a significant p-value for the alternative hypothesis that the mean is greater than 36 months, if we had been interested in that as an alternative hypothesis. So our conclusion is that we can say the mean of our random 10% sample does not equal 36 months and is less than 36 months. We cannot say that the mean is greater than 36 months. You may remember from Module 6, Topic 6, that the direction of the alternative hypothesis should be stated before the data collection begins and should be visible from the posed research questions. In the previous example, we tested whether the mean age of children in the sample was less than 36 months, which is a one-tailed or one-sided test, as is the other alternative hypothesis we saw in this data output that the mean age is greater than 36 months. When we don't have a hypothesis about the direction of the difference in means, we can use a two-sided or two-tailed test that states that there is some difference between means or that the mean does not equal the true value. One-tailed tests are more powerful than non-directional tests if findings are in the anticipated direction, but can be limiting or misleading if the findings are not in the anticipated direction. The example we just completed was for a one-sided hypothesis test, where we specifically wanted to know if the mean was greater than 36. Less than 36. Now we'll look at the same example, but assume that the mean age in months in the population is 31 months, with the same standard deviation of 17, and that we do not know whether the mean age of our sample will be greater than or less than 31 months. We can still use a z-test, but this time we'll use a two-sided hypothesis test because we want to know if our test value will be more extreme on either the lesser or greater end of the curve. We set our null and alternative hypothesis. In this case, the null is that the mean is equal to 31, and the alternative is simply that it does not equal 31. And we set the significance level again to 0.05. Now for a two-tailed test, the critical value of a z-test at alpha equal to 0.05 is plus or minus 1.96, as you can see in the far right column. This table can help you quickly reference the critical values for z for both one-tailed tests and the two-tailed test. When we enter our values in the equation, the test statistic we get is negative 1.66. When we use a z-score table, we know the p-value for negative 1.66 is 0.0485, and because this is a two-tailed test, we multiply this by 2 to get the total probability of getting our test statistic in both the lower and upper ends of the distribution, 0.097. We also know from the previous table that the critical value of z for an alpha of 0.05 is 1.96. That's the absolute value, so we can assess it the same way whether the test statistic is positive or negative. Given that the absolute value of negative 1.66 is less than the critical value of 1.96, and the probability of getting 1.66 on either end is 0.097, which is greater than the alpha of 0.05, this test is not statistically significant, and we fail to reject the null hypothesis that the sample mean age of 30.17 is different than the population mean age of 31. To show this on our distribution curve, we see that the critical value and the region of rejection for alpha equal to 0.05 are beyond 1.96 and negative 1.96, indicated by red shading. The value we obtained for our test was negative 1.66. We can see that 1.66 is not beyond or more extreme than the threshold or critical value of 1.96. The probability of obtaining 1.66 is 0.097, and the area covered by 0.097 is shown in the green hash marked area. We can run this data the same way we ran the previous z-test. You cannot set the z-test to greater than or less than. You can only set the command to equals because the test statistic is the same no matter the direction. We simply read the probability differently depending on whether it is a one-tailed or two-tailed test. In this case, we've only changed the mean age in months and set it to 31 months. We enter the command z-test in the command line with the variable cage, the equals sign twice to indicate is equal to, and then 31, and the SD or standard deviation is still 17. We run the command and we'll get the output you see here. We can check and see that it ran the z-test on 1,168 observations, and our observed mean age is still 30.17. Our 95% confidence interval for the point estimate of our mean is still the same. But we see that our z-score outputted below the table is negative 1.6506. At the bottom in the center, you can see that the p-value for the alternative hypothesis that the mean is not equal to 31 months is less than 0.0988, which is greater than 0.05, so we fail to reject the null hypothesis that the mean age is equal to 31 months. Our conclusion is that we cannot say that the mean of our random 10% sample is different than 31 months. Now, if we want to compare our mean age to the population norm, but we do not know the standard deviation of the population mean age, we use a t-test. T-test can be used when population variance is unknown. T is equal to the sample mean minus the population mean over the sample standard deviation divided by the square root of the sample size. To use a t-test table, we need to know the degrees of freedom of our test, which is the sample size minus 1. Here's how we calculate the t-test statistic. I'm not going to show you the student's t-table for which you can find the probability of the test value, but you can find that online if you'd like. The p-value for 1.648 is 0.0498 on each side, so the two-sided probability is 0.0995. This probability is greater than the alpha of 0.05 set for the test, and the critical value of 1.648 is less than the critical value of 1.96 for this t-test, so we fail to reject the null hypothesis that the mean age in months of our sample is different than the population mean of 31 months. If we conduct this test in Stata, we simply enter the command t-test with the variable cage and two equal signs, and then the population mean of 31. We don't know the variance, which is why we're using a t-test. When we run this, we see that we get the t statistic of negative 1.6484 with 1,167 degrees of freedom. Looking at the center bottom, we see that the probability of getting this t-value is 0.0995, which is greater than 0.05. Therefore, we cannot reject the null hypothesis. In summary, for a given sample with mean x-bar and a known population standard deviation of sigma, we can calculate the corresponding z-test statistic. We then determine the probability of obtaining a value that is as extreme or more extreme than our critical value of z, which is our p-value. If the p-value is less than the alpha we set, we would reject the null hypothesis. This test relies on the standard normal distribution and is called a z-test. Similarly, the t-test is used when the population standard deviation sigma is not known, but we know the sample standard deviation S. If the underlying population is normally distributed, we find the random variable we calculate will have a t-distribution with n-1 degrees of freedom. We calculate this test statistic t and find the probability, or p-value, of obtaining a value that is as extreme or more extreme than t. If this p-value is less than the alpha that we set, we would reject the null hypothesis. Most of the time, though, we're interested in comparing means of a variable or characteristic between groups. These groups might be those in the treatment and control group in a clinical trial, or between ethnic groups in health disparities research. We commonly compare characteristics between gender groups, and we should do this more often because most health interventions will affect women and men differently. Sometimes when we're comparing means of two populations, we examine two variables on the same individual, or we measure the same variable at two different time points on the same individuals. Let's consider the example of student stress level before and after an exam. We want to know, does stress level among students decrease after an exam? In order to test this hypothesis, we'll take a sample of 60 students and measure their stress levels indicated by the variable X before and after an exam. We use the same group of students before and after, so we know the stress level of the same student, both before and after the exam. In these paired samples, we have two measurements for each student, the stress level before, X1 before, and after, X1 after, the exam. Pairing is often used to control for variations between the subjects. When we compare the paired variables, we first calculate the difference of their means. Comparing whether the means are the same is equivalent to comparing whether the mean difference is 0. When we do this, it becomes a one-sample problem. If we can assume the differences are normally distributed, we can use what we already know to get confidence intervals, conduct hypothesis testing, and sample size calculation. Going back to the example, since the data are paired, we need to first calculate the difference in stress level before and after the exam for each student. We represent that difference here as D1, D2, and so on. Because we don't know the population standard deviation for the difference measure, we use t-distribution tests. To use t-distribution tests, we assume normality, so we assume the difference measure has a normal distribution. When this is not a valid assumption, for example, when the data are very skewed, we need to consider non-parametric tests that don't require normality, which we'll learn later. To perform a paired t-test, we need to first calculate the sample mean and sample standard deviation for the difference in scores before and after the exam among all the students in the sample. We can then calculate the t-test statistic as shown on the slide. In the numerator, we subtract 0 from the sample mean difference, because comparing whether the two means are the same for the paired samples is equivalent to comparing whether the mean difference is 0. Therefore, the null hypothesis is H0 mu difference equals 0. Under this null hypothesis, if the population of differences is normally distributed, the t-test statistic has a t-distribution with n-1 degrees of freedom. We calculate the p-value for observing a mean difference as larger than d bar. If the probability is less than or equal to the alpha we set, we can reject the null hypothesis. If p is greater than alpha, we fail to reject the null hypothesis. Let's take a look at another example now. It was difficult to find an example of this type of comparison within the mixed data, so we're using a random sample of individuals from the United States in a survey called the General Social Survey. In this survey, data were collected on each participant's father's education level, seen here as PA-EDUC, and mother's education level, variable MA-EDUC, in years of education. The other columns in this sample include the participant ID, their working status, how many hours they work per week, and their sex or gender. We test the hypothesis that the mean education levels among mothers and fathers are equal. To do so, we let delta represent the mean father's education in years minus the mean mother's education in years. The null hypothesis is that this mean is equal to 0. This mean difference is equal to 0, or there is no difference on average between father's education in years and mother's education in years in the general social survey. Because the values of the two populations, mothers and fathers, are paired within each participant, the test is a paired t-test. The Stata code to test this hypothesis is simply t-test, and the father's education variable is equal to mother's education variable. Here's the Stata output for the paired t-test example. First, we see the null hypothesis of this test, which is H naught delta equals 0 or mean difference equals 0. We can look at the mean education level in years for fathers and mothers in the data set and see that the mean value for mothers is a bit higher than for fathers, but we don't know if that's a significant difference. Next, we look at the difference in mean education levels among the 1,903 observations that were used in this test, which is equal to negative 0.16. We can see the sample standard deviation of the difference is 3.18, and that the t-test statistic is negative 2.219. Finally, we look to see the p-value for the two-sided hypothesis test with alternative hypothesis that the mean difference does not equal 0. In other words, the education levels of mothers and fathers are not equal. We can also see that the p-value for the one-sided t-test of the alternative hypothesis mean difference is less than 0 is also significant. This demonstrates that the average education level of fathers is significantly less than that of mothers in this sample. Another way to perform paired t-test in Stata is to generate a difference variable called diff here that is equal to the difference between fathers and mothers' education for each participant. For example, the difference between fathers and mothers' education for the individual with ID number 5 is 16 minus 10, which gives us a value of 6 for diff. Then a paired t-test can be performed just like a one-sample t-test with the null hypothesis delta equals 0. Please note that the output of this one-sample t-test is exactly the same as the lower part of the Stata output from the paired t-test shown on slide 36, because these two tests are equivalent. In the previous slides, we discussed how to perform paired t-test for paired samples. In practice, more often we are given a sample from each of two independent populations of interest. The sample sizes may or may not be the same. We'll call the sample size of the first sample as N1 and for the second sample of N2. Each of our two samples will contain a sample mean, x bar, and a sample standard deviation, S. Each sample will also have a population mean, mu, and a population standard deviation, sigma. Our interest is to compare mu1 and mu2, and the method we use, the two-sample t-test, depends on whether we can assume the variances for both populations are equal. There are two methods for comparing these two means. Method 1 is to assume that the variances or standard deviations are equal. Method 2 does not assume equal variances. Method 1 is easier to use, but requires that the variances are, in fact, equal. But Method 2 is just as easy as Method 1 when you have software. Both methods typically give quite similar answers unless both the sample sizes and the sample standard deviations are very different. We use a two-sample t-test when we are comparing two independent groups. That is, groups that are not paired when we have continuous measurements such as weight, height, blood levels of a nutrient or a toxin and such, and when the population distribution of the measurement are approximately normal. Here is an example from the mixed random sample that you can follow along with in Stata if you'd like. This box plot shows the distribution of BMI of children who participated in the polio vaccination campaign on the left and of those who did not participate in the polio vaccination campaign. Does the distribution look similar to you? Does it look normal? We can conduct an independent samples t-test in Stata to see if the mean BMI for children who participated in the polio vaccination campaign is equal to the mean BMI of children who did not participate in the polio vaccination campaign. To do this, we use the t-test command and type into the command line t-test BMI if BMI less than 40 by IM8A, which is the dichotomous variable for participation in the polio campaign. We are specifying BMI less than 40 to ask Stata to remove any BMI greater than 40 from this test because of extreme outliers. We can see that the hypothesis is that the difference in means is equal to 0 or that there is no difference. We get a test statistic of 0.4408 with 317 degrees of freedom. The probability of obtaining this value, if the mean difference is not 0, is 0.6596, which is not less than the default alpha of 0.05. But we are assuming in this test that the variances are equal in both groups. What happens if we do not assume variances are equal? To assume variances are not equal, we use the same t-test command, but add unequal to the end of the command text. You can see that the test statistic is slightly different than the one calculated when assuming equal variances, but not by much. There's still not a significant result. Therefore, we would still fail to reject the null hypothesis that there is no difference between the mean BMI of each group. But how do we know which test to use? To test whether the standard deviations are equal, we use the sdtest command and enter the rest of the variables as we did in the t-test commands. This will test the null hypothesis that the standard deviation ratio is equal to 1. That is, that the standard deviations for both groups are the same or equal. If we have a significant result, as we do here, then we reject the null hypothesis that the standard deviations are equal or the same, and we assume that they are not equal and therefore must report the results of the unequal variances test. As a summary, when we want to compare two population means, we need to first identify if we have paired samples or two independent samples. If paired samples, we should use paired t-tests. If two independent samples, we need to first determine if we can assume the population variances are equal or not. If yes, we should use the two-sample t-test with equal variances. Otherwise, use the two-sample t-test with unequal variances. What if we have more than two samples? We can still perform all pairwise comparisons between the samples in questions. If we had 3 samples in our study, we could conduct 3 pairwise tests between 2 groups each. For 4 groups, we could conduct 4 pairwise tests, and so on. For example, if we wanted to study the weight of students as a function of time at a university and understand whether the average weight for each group of students by year in university is the same, we assume time is a discrete variable and we measure it as year 1, year 2, year 3, and year 4. We can use 2 sample t-tests to compare each pair of groups, which would mean that we need to conduct 6 tests overall. But rather than do this, we can conduct a one-way analysis of variance, or ANOVA. In this type of analysis, we compare the variability of the observations within sample as well as between samples. If these 2 variances are comparable, we conclude that there is no difference among the groups. If they are not comparable, then we conclude that there is a significant difference among the group means. In this graph, we try to compare the means of 4 groups where the 4 black lines depict the group means of the 4 groups, and the dots of each color represent the data collected from each group. In other words, the yellow dots are the values sampled from the first group, the year 1 students, the green dots are the values sampled from the second group, and so on. The red line represents the mean of all the dots in different colors. On this slide, the variance among the lines is much larger than the variance among the dots within each group. Hence, the dots with different colors are all well separated. In this situation, the ratio between variance of lines and the variance among the dots within each group would be a relatively large number, much larger than 1. On this slide, the variance among the lines is about the same as the variance among the dots within each group. Hence, the dots with different colors are mingled together on the slide. In this situation, the ratio between variance of lines and the variance among the dots within each group would be a relatively small number, quite close to 1. The variance among the dots within each group is called within group variance. If we are only comparing 2 groups, then the formula is actually the same as the formula for pooled variance that we learned in a 2-sample t-test. But note that this means we are making an assumption about the quality of variance among the groups. To estimate the within group variance, we obtain deviations of data within each group of interest. That's why we use the name within group variance. If we have k groups, the within groups variance would be represented by this formula. To calculate the between group variance, we measure the distance of the lines or group means from the grand mean using the following formula, where x bar is the grand mean shown here as the red line, and each x bar subgroup is the mean of each group. If the variability of the lines from the grand mean, or the between group variance, is greater than the variability of the dots from each group mean, or the within group variance, then the ratio will be large. But if the between group variance is smaller than the within group variance, then the ratio will be small. This is the F statistic with an F distribution. The between group variance has k-1 degrees of freedom, and the within group variance has n-k degrees of freedom. Hence, the F statistic has k-1 and n-k degrees of freedom. The null hypothesis of ANOVA is that all the group means are equal. The alternative hypothesis, then, is that at least one group mean does not equal the others. As with all of our test statistics, if our F statistic is extreme enough beyond the critical value, we reject the null hypothesis and accept that there is a significant difference among the group means. In this slide, we are looking at the frequency, mean, and standard deviation of child's weight by 5 different ethnic group categories in the random mixed sample. There is a total of 1,160 observations, and again in this test, those with a BMI of 40 or above are removed from the analysis. The grand total mean is 11.0 kilograms with a standard deviation of 3.2 kilograms. I've pasted the complete names of the ethnic groups here because Stata cuts the text off, and I wanted to make sure you could read all of the categories properly. We can see here that the values for the sum of squares, SS, and the mean squares for between and within groups, and their degrees of freedom, all of which make up the F statistic. The value of the F test is 5.92, and the p-value is 0.0001. Therefore, there is a significant difference in the means of child's weight by ethnic group. The post hoc Bonferroni comparison conducts the pairwise mean comparisons that we mentioned in the beginning of the ANOVA section and provides p-values for these comparisons. The value you see here is the row mean minus the column mean. So the value circled in red shows that the Lao Thai ethnic group mean weight was 1 kilogram greater than the mean weight of the Hmong Khmer ethnic group, and the 0.000 beneath this negative 1.0 value is the significance level of this difference from a difference of 0. Therefore, we can see that these two group means are significantly different, but the other group means, all of which have p-values greater than 0.05, are not. Here is practice that you can do on your own in Stata. Is there any evidence to believe that kids in different ethnic groups differ in terms of their average BMI? Test this hypothesis using the techniques we discussed here in this training. This has been a very dense section with quite a bit of review from Module 6, but applied to the mixed data and using Stata software. To summarize, in this section you've learned the following. To compare means between a sample and population, we can use a z-test or a t-test if we do not know the population variance. To compare means between groups that are paired, which may mean 2 variables in the same individual at the same time, or 1 variable at 2 times for the same individual, we can use a paired samples t-test. To compare means between independent groups, we use an independent samples t-test. To compare means among more than 2 groups, we use a one-way ANOVA and can add post hoc tests to better understand where the differences exist. Final thoughts. Hypothesis testing involves determining whether some finding in our data is likely or unlikely to occur if the null hypothesis we propose is true. Using Stata, you can now easily test hypotheses comparing means of groups or populations and samples. Thank you.